Welcome to the Deep Dive. We're the place where we really plunge into some fascinating research, cutting through the noise to bring you the insights that, well, that really matter. Just imagine your home right now. You've probably got a smart thermostat, maybe a voice assistant playing music, security cameras, maybe even a fitness tracker on your wrist. All these devices, they're just humming along, seamlessly connected, constantly swapping data. We are absolutely living in the age of the Internet of Things. It's this huge interconnected web, billions and billions of devices all talking. There was a Cisco forecast back for 2021, something like 27.1 billion connected devices. I mean, that's just astounding, more than 3 times the number of people on the planet. So that's everything from your smart doorbell to industrial sensors in a factory, fitness trackers, even traffic lights in a smart city. They're all part of this network. It's great, right? It's all about convenience, automation, making life, well, simpler. But, and there's always a but with revolutionary tech. With all this convenience comes this massive lurking security challenge. How do you really know that tiny sensor or that smart lock or even your wearable isn't compromised? Or worse, being impersonated by an attacker right under your nose?
Yeah, that's the million-dollar question, isn't it? Or maybe the billion-device question.
Exactly. And that's the critical problem we're really here to tackle today. The usual ways, the traditional authentication methods in IoT, things like digital signatures or HMACs, even protocols like OAuth 2.0 that you see in systems like, say, Google's Nest. These are the building blocks, sure, but they're surprisingly vulnerable to really sophisticated attacks.
Yeah.
We're talking key recovery, where someone literally steals the cryptographic keys, or cross-site request forgery, even just physically hacking the device open to get the secrets out.
Right, invasive attacks.
Yeah, and not only are they vulnerable, but these methods can be, well, cumbersome, resource-intensive, especially for those tiny, low-power, cheap devices that make up most of the IoT.
You can't stick a high-end security chip in every single light bulb. It's just not feasible. The cost, the power drain.
Precisely. Wouldn't be practical at scale. So today, we're diving deep into a really fascinating, innovative solution. It comes from a paper by researchers at Purdue University. The title is RF-PUF, Enhancing IoT Security Through Authentication of Wireless Nodes Using In Situ Machine Learning. And our mission for you, the listener, is to unpack how these seemingly undesirable manufacturing imperfections, tiny flaws, how those, combined with machine learning, could fundamentally change how we secure our connected world, making it, well, virtually impossible for an imposter to sneak into your network. And the kicker, without adding extra cost or complexity to the devices themselves.
It's an incredibly timely topic. And, what's truly fascinating here is how it flips the script. Instead of fighting against hardware imperfections, which is what engineers usually do, right? Trying to make everything perfect, identical, this research actually proposes embracing them, using those tiny, unavoidable variations as a unique identifier.
Turning a flaw into a feature.
Exactly. It turns what we normally think of as a flaw in electronics into a security feature, a really robust one. Because the scale of the IoT security problem is just immense. And the limitations of current methods, especially for these really tiny resource-constrained devices, they're becoming painfully clear. This paper, it offers a genuinely innovative shift in thinking, a path forward that feels both powerful and, actually practical.
Okay, so to really appreciate what RF-PUF is doing, we first need to grasp the scale of the security problem it's trying to solve. The Internet of Things, it hasn't just grown, it's exploded, hasn't it? That 27.1 billion device number from Cisco, it's almost hard to comprehend.
It really is. You start thinking about it.
Yeah, picture this sprawling digital ecosystem. Your smart thermostat learning your schedule, critical sensors, monitoring pipelines, maybe network medical devices, tracking vital signs, even just the humble smart plug controlling a lamp. Every single one, from the mundane to the mission critical, is a potential doorway for an attacker.
And they're not sitting in secure data centers.
Exactly. They're out in the world. In our homes, on our bodies, in factories, on streets. Untrusted environments, basically. Constantly exposed.
Which makes them prime targets.
Imagine the chaos if someone could spoof your smart smoke detector, or mess with the city's traffic grid, or even just subtly change the data from a health sensor you're wearing.
The consequences could be severe.
So this pervasive presence makes security absolutely critical. But it's also incredibly challenging given how diverse these devices are and how little power or memory they often have. So let's talk about the traditional ways we've tried to secure them. The standard approach, you mentioned keys.
Right. Usually you embed a secret key, like a unique password or a cryptographic seed, into the device's memory. Often it's non-volatile memory, NVM, which keeps the data even when powered off, or sometimes battery-backed SRAM, which is faster but needs constant power.
And this key is then used for things like digital signatures to prove a message is authentic or for encryption, right?
Correct. It verifies the device's identity and ensures only trusted devices are talking on the network. Seems secure on the surface, like a digital key for a door.
But you said it's vulnerable.
Unfortunately, yeah. While these methods are foundational, they're susceptible to a whole spectrum of pretty sophisticated attacks. We often lump them together as key hacking.
And that's not just guessing passwords.
Oh no, definitely not. We're talking advanced techniques.
Yeah.
You have invasive attacks. That could mean literally decapping the chip, removing its protective layer. Then using microscopic probes to physically read the data right off the memory. It's like microsurgery on the chip.
Wow.
Then there are semi-invasive attacks, maybe using focused lasers or UV light to interact with the memory, trying to slip bits or read them out without full destruction. Less obvious.
Okay.
Then you've got software attacks, exploiting bugs in the device's firmware or the operating system to gain access to the memory where the key is stored.
Good.
No physical tampering needed there.
Right, finding a backdoor in the code.
Exactly. And then there's a particularly sneaky category. Side channel attacks. These are really clever. Attackers don't go for the key directly. Instead, they watch the device operate. They might measure its power consumption while it's encrypting something.
How does that help?
Well, the exact power used can subtly change depending on the calculations being done, and those calculations depend on the secret key. Or they might analyze the electromagnetic fields the chip gives off, or even tiny, tiny differences in the timing of operations.
So they're inferring the key from these side effects.
Precisely. By carefully analyzing these side channels, they can deduce the secret key without ever touching the memory itself. It's like figuring out a safe combination by listening to the clicks, not by drilling it open.
That's ingenious, but also kind of terrifying from a security perspective.
It absolutely is.
And it's not just these low-level hardware attacks. Even higher-level protocols, like OAuth 2.0, that's used a lot in IoT, right? Like how your Nest thermostat talks to the cloud or your phone app.
Yes, it's a common standard for authorization.
Well, the paper mentions that even that suffers from vulnerabilities, specifically cross-site request forgery, CSRF attacks. What does that mean in an IoT context?
Okay, so a CSRF attack basically tricks your browser while you're logged into a service into sending a command that you didn't intend to send. In IoT, maybe an attacker tricked your browser into sending a command to unlock your smart door or turn off your security camera using your authenticated session, all without you knowing.
Yikes. Okay. And the paper also mentions OAuth 2.0 can become cumbersome.
Yeah, from a user perspective, as you get more and more devices, imagine having to manually authenticate every single smart bulb, every sensor, every appliance you add to your home network, one by one.
It would get old fast.
Very fast. It leads to user fatigue, and often people start taking shortcuts, maybe using weak passwords or disabling security features just for convenience, which defeats the purpose.
So connecting this all together, what's the big picture consequence of these vulnerabilities?
The bottom line is, an adversary could potentially copy or figure out those secret IDs or encryption keys. And once they have the key, they can impersonate a legitimate device, they can inject fake data, take control of devices, maybe even disrupt the whole network.
Real-world impact, privacy breaches, maybe even physical safety issues.
Absolutely. And for most IoT devices, remember, they're built to be cheap and use minimal power. They just don't have the resources for complex security hardware. Things like secure hash algorithms, public-private key encryption, tamper-resistant memory. These things add cost, take up space on the chip, and drain the battery.
So there's this fundamental tension.
Exactly. Manufacturers want cheap, small, low-power devices. But strong security traditionally needs more resources. You square that circle. The existing solutions often just don't fit the bill for the lightweight, pervasive nature of the IoT.
So it's pretty clear. Security development for this kind of mobile embedded hardware hasn't really kept pace with the explosion of devices or their computing power. There's a gap, which raises that fundamental question. Is there a different way? Something that works with the limitations, maybe even the imperfections of these devices, instead of fighting them?
Can we bake security into the physics, maybe, instead of just adding a vulnerable digital layer on top?
Okay, let's unpack this core concept then, the one that RF-PUF builds on. Physical unclonable functions, or PUFs. This is where the real ingenuity starts. So at its heart, what is a PUF doing?
Well, basically, a PUF takes advantage of the tiny, unavoidable variations that happen during the manufacturing of silicon chips. Think of it like this. When they make chips, even in the most advanced factories, The process isn't perfectly identical every single time down at the microscopic level.
Like tiny differences in material density or the exact size of transistors.
Exactly. Uncontrollable, random variations. So no two chips, even from the same wafer, are exactly alike physically. PUFs harness these subtle, random differences to create a unique fingerprint for each individual chip, a device-specific identity based on its physical structure.
Okay, like a biological fingerprint, but for silicon.
That's a great analogy.
The paper uses another really elegant analogy, comparing it to the human voice. Can you explain that?
Yeah, it's a really helpful way to think about it. They say, think about how we identify each other by voice.
Mm.
When someone speaks, you don't just understand the words, what they're saying. You often instantly recognize who is speaking.
Based on their pitch, tone, cadence, their unique vocal characteristics.
Right, their unique voice signature. This RF-PUF research takes direct inspiration from that very human ability discerning identity from an analog signal, even if the message itself is new. It's about recognizing the source, not just the content.
That makes sense.
And what's really fascinating, building on that voice analogy, just like your brain does the hard work of identifying the speaker from their voice, without the speaker needing special voice signature generating hardware, this RF-PUF system shifts all the identification burden to the gateway receiver.
So the little IoT device, the transmitter, doesn't need any extra hardware to create this unique ID.
Correct. It's just an inherent property of its radio frequency output. The intelligence, the machine learning that detects and verifies that physical signature, it all lives at the receiver.
Which is usually a more powerful device anyway, like a router or a dedicated gateway.
Exactly. It's an asymmetric solution. It offloads the complexity, the processing, the power consumption from the tiny, constrained device, which is a huge win for IoT. The paper's figure 1 really visualizes this nicely, Alice speaking, Bob identifying her voice, right next to an IoT transmitter, and the receiver's ML engine doing the same thing, listening to how it speaks, not just what it says.
Okay, so the core advantage is this inherent unclonability, because it's tied to the physical manufacturing randomness.
Precisely. It's practically impossible to replicate the exact same microscopic silicon characteristics across different chips. These variations are just a natural byproduct of incredibly complex fabrication processes.
Even in those ultra-clean, high-tech semiconductor plants.
Even there.
Yeah.
At the nanoscale, quantum effects and statistical variations are just inevitable. Trying to clone a PUF would mean replicating the manufacturing process with absolute atomic-level precision for that specific chip's random flaws.
Which sounds difficult.
Astronomically difficult.
And
expensive. It's technically infeasible for an attacker. So this inherent physical randomness makes a PUF-based system extremely robust and secure at low cost. There's no secret digital key stored somewhere vulnerable. The secret is the physical device itself.
Okay. Now, you mentioned PUFs can be weak or strong. What's the difference and why does it matter here?
Right, that's an important distinction for security. It's based on the number of challenge response pairs, or CRPs, they can handle. Think of the CRP like this. You give the PUF an input, a challenge, and it produces a unique output, its response, based on its physical structure. A unique question leads to a unique answer for that specific PUF.
Okay.
Weak PUFs have a relatively small, limited number of possible CRPs. Maybe the number grows linearly with some parameter. If an attacker can observe enough of these pairs, they might be able to build a statistical model and predict future responses.
Which compromises the security.
Right. Strong PUFs, on the other hand, support a vast number of CRPs, often growing exponentially. We're talking huge numbers. This makes it computationally infeasible for attacks that try to model the PUF in polynomial time. An attacker simply couldn't gather enough data or have enough computing power to reliably predict responses.
An RF-PUF aims to be a strong PUF.
Yes, exactly. That's crucial for device authentication in a massive IoT network. You need that enormous number of potential responses to make sure devices can be uniquely identified, and that an adversary can't easily guess or forge a device's identity.
Okay, this is where it gets really interesting. RF-PUF isn't just a general PUF concept. It's a specific, practical framework, using a deep neural network for real-time authentication of wireless devices.
Right. And instead of relying on memory-based PUFs or other types, it focuses specifically on the radio frequency properties. It exploits how those inherent manufacturing variations affect the way a device transmits wireless signals.
So those tiny physical flaws leave a unique trace on the radio waves themselves, like an accent, you said.
Exactly like an accent. A subtle but unique and measurable physical characteristic imprinted on every signal it sends.
And you mentioned some key advantages, especially for IoT. The first one sounds huge. No additional hardware on the transmitter side.
Monumentally huge, yes. This method uses the RF communication system that's already there in every wireless device. It doesn't need any extra circuits just for generating the PUF signature or extracting features on the transmitter itself.
Which means for those tiny, cheap, low-power IoT devices.
It's a game changer. No added cost, no extra space on the circuit board, no extra battery drain on the device itself. You're using its intrinsic physical nature. That makes it instantly much more viable for mass deployment.
So why hasn't this been the standard approach all along? It seems so elegant.
Well, it goes back to that mindset shift. Engineers have traditionally worked incredibly hard to minimize these non-idealities, these tiny variations in analog and RF properties. They were seen as noise, imperfections to be filtered out or compensated for, not features to be used.
Right, you want predictable, identical performance usually.
Exactly. RF-PUF flips that. It says, hey, these imperfections are actually a sort of unique randomness of entropy. Let's use them. It turns that unavoidable manufacturing variance into the very thing that creates a strong, unique identifier. It's leveraging what's already there, which is very smart engineering, especially for cost-sensitive IoT.
Okay, so the transmitter is simple. The identification happens at the receiver, the RX, using machine learning.
Right. Just like your brain processing a voice, the receiver, typically a more powerful gateway, runs the machine learning model. It does the heavy lifting. It listens to the incoming RF signal, detects that subtle physical fingerprint, and verifies the sender's identity in real time.
And the paper claims this is the first work doing this in a specific way, preamble-less.
Yeah, they highlight it as the first work in this area for low-cost, preamble-less, intrinsic PUS-based authentication of IoT nodes.
What does preamble-less mean here? And why is it significant?
Okay, so traditional RF fingerprinting often relies on the preamble. That's a fixed, known sequence of bits at the very start of a data packet. Systems use that predictable part to extract features. RF-PUF avoids needing a known preamble. It can authenticate based on the characteristics of the actual data transmission itself, even if the data is random or unknown.
Ah, so it's more flexible, but maybe faster.
More flexible, potentially faster, because you don't need to wait for or process a specific preamble, and potentially more secure because it doesn't rely on a predictable fixed pattern that an attacker might also know or try to manipulate. It authenticates on the fly.
Okay, and the performance. The abstract mentions some impressive numbers.
Yeah, the simulation results are quite striking. They showed it could distinguish up to 4,800 transmitters with 99.9% accuracy.
Wow.
And even scale up to 10,000 transmitters with around 99% accuracy. And this is even when simulating varying channel conditions like noise or signal fading.
So for a typical smart home or even a decent-sized industrial network, that's incredibly reliable identification.
It suggests it could provide a very strong foundation of trust, making it extremely difficult for an attacker to impersonate one of those thousands of devices.
How does this fit in with existing security? Is it a replacement or something else?
It offers a lot of flexibility. It could be used as a standalone security feature right at the physical layer, the most fundamental level of communication, a baseline layer of trust. Or, perhaps more likely in many scenarios, it could be integrated as part of a multi-factor authentication approach.
Like, you still have your password or network key, but the router also checks the device's physical RF fingerprint.
Exactly. It augments the existing security at the network, transport, or application layers. It adds this hard-to-spoof physical identity check, like adding a biometric scan to your password login.
Makes sense. And the paper hinted at broader applications beyond just authentication.
Right, because you're essentially identifying the unique physical source of a signal. They suggest it could be used for things like intrusion detection, spotting rogue devices trying to join the network because their RF signature doesn't match any known legitimate devices. Forensic data collection, if there's an incident. Maybe you can trace the physical device responsible based on its unique signature captured in logs. Even defect detection or monitoring. Perhaps as a device ages or starts to fail, its RF signature might subtly change over time. You could potentially predict failures.
Like predictive maintenance based on its radio voice changing.
Kind of like that, yeah. And they also mention applications for sensitive things like body-connected biosensors, ensuring the data is coming from the correct, legitimate sensor on the patient. It establishes trust right at the physical edge.
Okay, let's really dig into the nuts and bolts now. How does RF-PUF actually work? We know it embraces manufacturing variations because, as the paper says, tightly controlled fabrication is expensive. It's cheaper to leverage these inherent non-idealities.
Exactly. Cost efficiency is paramount for IoT.
So what specific RF features is it using to create these fingerprints? You mentioned a few key areas. The first was frequency features, related to the local oscillator offset.
Right. Every wireless transmitter has a local oscillator, or LO, to generate its carrier frequency. Think of it as the baseline radio wave. But due to those tiny manufacturing variations, no two LOs are perfectly identical. They all have a slight unique frequency offset, a tiny deviation from the ideal target frequency.
Like each radio is slightly uniquely out of tune.
Precisely. Even within very tight standards, like
Yeah.
the IE 802.11b Wi-Fi standard, which requires the offset to be within plus or minus 25 parts per million ppm, which is incredibly small. Each device still has its own specific measurable offset within that tiny range. It's a unique signature.
And how does the receiver detect this tiny offset? Does it need special hardware?
That's the clever part, no. The receiver already has a module called a carrier synchronizer. Its normal job is to detect and compensate for this LO offset anyway, just to ensure reliable communication.
So it's already measuring it.
It's already measuring it. RF-PUF just takes that measured ppm value and feeds it as a feature into the neural network for identification. It repurposes an existing function for security. Very efficient.
Okay, frequency offset is one feature. What about the IQ features? Amplitude and phase imbalance. What are I and Q?
Okay, so in many digital radio systems, to pack data efficiently onto the radio wave, the signal is split into two components. In phase,
Yeah.
I, and quadrature Q. These are essentially two waves that are 90 degrees out of phase. Together, they carry the data. Ideally, these I and Q components should be perfectly matched in amplitude, strength, and exactly 90 degrees apart in phase.
But in reality,
In reality, due to those same manufacturing variations in the analog circuits, there's always a slight mismatch. The amplitude might be slightly different, or the phase difference might not be exactly 90 degrees. And this IQ imbalance is unique to each transmitter device.
how does that show up at the receiver?
It visibly distorts something called the constellation diagram. That diagram is a plot of the received signal points, which represent the data symbols. With IQ imbalance, instead of seeing nice, tight clusters of points where they should be, you see a smeared or skewed pattern. And weight skewed is unique to the transmitter. Figure 3 in the paper shows this distortion quite clearly. Other things like variations in the power amplifier also contribute. So the system needs to look at the amplitude and phase of all the received symbols to capture this rich, unique distortion pattern. It's like analyzing a device's specific signal handwriting.
Okay, so we have frequency offset, IQ imbalance. These are inherent to the transmitter. But what about the journey this signal takes? The communication channel itself adds noise, distortion.
Right, the channel is a huge variable. The signal gets weaker with distance, attenuation. It can bounce off walls, causing echoes, multipath distortion. And if the device or receiver is moving, you get Doppler shift.
So how does RF-PUF make sure it's identifying the device and not just the channel the signal passed through?
That's absolutely critical. The system must estimate and compensate for these channel effects. Otherwise, the channel noise could completely swamp the subtle device signature.
And again, does it use existing receiver parts?
Yes, thankfully. Standard wireless receivers already have components to deal with this for reliable communication. There's an automatic gain control, AGC block, to handle varying signal strength. There's usually a filter, like the root raised cosine RRC filter mentioned in the paper, to reduce inter-symbol interference. That's when symbols blur together.
Okay.
And there's often a Doppler corrector for movement. Figure 4 shows this receiver chain. The key is that these modules estimate the channel affects the attenuation, the Doppler shift, and this information is also fed into the artificial neural network, ANN.
So the neural network learns to distinguish between the device's fingerprint and the channel noise.
Exactly. It learns what variations are due to the environment versus what variations are intrinsic to the specific transmitter. It learns to filter out the noise and focus on the true signature. It makes the system robust to changing real-world conditions.
Okay, that brings us to the machine learning framework. The brain at the receiver. It's a 3-layer neural network, you said. Relatively simple.
Architecturally, yes. Not some massively complex deep learning model, which is good for efficiency, but how it's trained is innovative. You mentioned preamble-less training.
Right. The paper calls this a key differentiator instead of relying on those fixed preambles.
It's trained using multiple iterations, and each time it uses different pseudo-random bit streams as the data.
Why is that important?
It's crucial because it means the network learns to identify the transmitter based on its RF characteristics, regardless of the actual data being sent. It doesn't need to see a specific known pattern like a preamble. This makes authentication possible on the fly during normal data transmission, much more practical for IoT devices sending varied data. Figure 5 visualizes this training process.
You said the training also uses different channel conditions.
Yes. Each training iteration doesn't just use different random data, it also simulates slightly different channel conditions, different noise levels, maybe different signal paths. This is fundamental. It teaches the network to generalize, to recognize the device's signature despite environmental variations. As we just discussed, it learns to separate the signal from the noise.
How much training are we talking about?
The paper mentions using 10 training iterations, each with a pretty long data stream, 30,000 bits. So it's like giving the network 10 different practice runs, each with a new random script and a slightly different environment. This iterative, varied training is what builds a robust system that can reliably pick out those subtle physical differences across potentially thousands of devices in messy, real-world conditions. It's a sophisticated learning approach for a practical result.
Okay, so for RF-PUF to be more than just a cool idea, for it to be genuinely useful for security, it needs to have certain core properties. These define what makes a PUF, especially a strong PUF, effective.
Absolutely. These aren't just academic checkboxes, they're essential for real-world viability.
Let's run through them. First, constructability.
Right. This just means there has to be a way to create the PUF. For RF-PUF, the creation procedure is the standard chip manufacturing process itself. The inherent random variations during fabrication automatically construct the unique physical properties. It's built in.
Okay. Then evaluability.
This means you need to be able to get a response from the PUF when you give it a challenge. Here, the challenge is the digital bit stream the transmitter sends. The response is the resulting analog RF signal, carrying that unique physical fingerprint embedded within it. The receiver evaluates this response.
Makes sense. Next, reproducibility or reliability.
This is key. The same device, when challenged multiple times, should ideally produce the same response, or at least a very, very similar response, even if things like temperature or voltage fluctuate a bit. This measures the intra-PUF variation, how much a single device's signature wobbles over time. You want this wobble to be minimal for reliability.
And the flip side is uniqueness.
Exactly. Different devices, even if given the same challenge, sending the same data, must produce significantly different responses. This measures inter-PUF variation, how different the signatures are between devices. You need high inter-PUF variations so you can tell devices apart.
And the crucial balance between these two is identifiability.
Right. Identifiability is achieved when the inter-PUF variation, the wobble of a single device, is consistently much smaller than the inter-PUF variation, the difference between devices. The paper showed promising results here. For 1,000 simulated transmitters, the worst-case difference between devices, inter-PUF, was about 3.9 ppm, while the variation within a single device, inter-PUF, was around 2.9 ppm.
So the difference between devices was clearly larger than the noise within a single device's signal.
Yes, which is a strong indicator that the system can practically and reliably tell devices apart. Like recognizing voices, your voice might vary slightly depending on your mood, but it's still clearly different from my voice.
Okay. And finally, PUF strength. This sounds important, especially for security against modeling attacks.
Immensely important. This relates back to the number of possible challenge response pairs, CRPs. Because the RF features are analog values, the potential response space is enormous. Theoretically, it's RM, where M is the number of features and R is the set of real numbers.
Which is infinite.
Theoretically, yes. But even if we think practically, say the receiver measures these analog features using a 16-bit analog-to-digital converter, ADC. That gives 216 possible discrete values for each feature. If you just use 5 different features, the total number of possible CRPs becomes 2 to the power of 16 times 5, which is 280.
2 to the power of 80. That sounds big.
It's astronomically big. It's a number larger than the estimated number of atoms in the observable universe.
Wow. Okay. So what does that mean for an attacker?
It means if they try to build a model to predict the device's responses, even if they observe responses from, say, 9 different challenges, the chance of them correctly predicting the response to the next challenge is incredibly tiny, like 1 divided by 280 or 216 meters generally. This extremely high dimensionality is what makes RF-PUF a strong PUF. It makes statistical modeling attacks computationally infeasible. You just can't gather enough data in a reasonable time to crack it.
Okay, so the theoretical properties look solid. How did it actually perform in their simulations? You mentioned the accuracy numbers earlier.
Right, using a standard 16 QAM modulation and simulating 65mm chip variations, they got really good accuracy. Less than 1 in a 5 inch randers of a false detection. excepting an imposter, for up to 4,800 transmitters.
And still around 1 in 100 for 10,000 transmitters. Figure 6A showed that.
Yeah, which is pretty remarkable for that scale, especially considering channel variations were included. It suggests very reliable authentication for typical IoT deployments.
Did they optimize the neural network itself?
They did. Figure 6b shows they tested different numbers of neurons in the hidden layer of the ANN. They found a sweet spot around 50 to 100 neurons. Going beyond that didn't significantly improve accuracy, but would add computational cost and power consumption at the receiver. So they found an efficient balance.
And what about the impact of that preamble-less multi-iteration training? Did it prove effective?
Yes, Figure 6c really highlights that. As they increased the number of training iterations using that varied, random data, the system's performance, especially in reducing false rejections, got better and better, eventually matching or even slightly beating a system trained only on a fixed preamble. But crucially, it gained the ability to handle varying channel conditions, which the fixed preamble training wouldn't learn as effectively. So the flexible training led to robust real-world performance.
What about noise? How robust was it?
They looked closely at that. Figure 6T specifically shows the importance of that RRC filter, the root raised cosine filter at the receiver. Without it, noise and intersymbol interference caused an error probability of about 0.02 or 2%, which isn't great.
But with the filter.
With the RRC filter cleaning up the signal, the error rate dropped dramatically to 10 to 5. That's 0.0001%, a huge improvement in reliability. It shows how standard signal processing components are vital to making the PUF extraction reliable.
And figures 6E and 6F tried to visualize the reliability and uniqueness directly.
Yeah, those plots are interesting. Instead of just error rates, they plotted the distance between signatures. They calculated the geometric mean of the normalized ppm variations for the features. They showed the intra-PUF distance, variation within one device over time, and the inter-PUF distance, variation between different devices. The key finding, visually clear in the plots, is that the inter-PUF distances were consistently much larger than the intra-PUF distances.
Confirming that devices are distinct and relatively stable in their signatures.
Exactly. It's visual proof of the system's ability to discriminate reliably.
Okay, one more performance check.
Yeah.
Randomness. Security systems need unpredictable outputs. Did they test that?
They did. They subjected the output bits generated from the RF-PUF process to the standard NIST statistical randomness tests. These are rigorous tests looking for biases or patterns. Figure 7 shows the results. RF-PUF passed 15 different NIST tests with rates consistently above 0.9, which is very close to NIST's own benchmark for random bits. It also passed the basic frequency test with over 95% success.
Meaning the output looks genuinely random and unpredictable?
Yes, it confirms strong randomness and low bias, which are essential cryptographic properties. The physical fingerprints aren't easily guessable or predictable.
Now, this was all simulation. Did they try it with real hardware?
They did, which is a crucial step towards proving practicality. They set up an experiment using software-defined radios, SDRs, shown in Figure 8.
SDRs are like programmable radios.
Exactly. Very flexible. They couldn't easily get thousands of unique manufactured IoT devices, so they used SDRs and emulated different transmitters. They did this by carefully controlling and changing the ambient temperature around the SDRs. Temperature affects electronic components, subtly changing their RF characteristics.
So changing the temperature created slightly different unique RF feature sets for each emulated transmitter.
Precisely. They created 10 distinct emulated transmitters this way. And the neural network successfully identified all 10 based on these subtle, temperature-induced RF feature differences.
So it worked on real hardware, even with these small, artificially created differences.
Yes, it's a strong proof of concept, showing the system can distinguish real-world RF signals based on these fine-grained physical characteristics. Of course, it also points to important future work, needing robust calibration for real-world environmental factors like temperature and voltage swings over long periods, maybe by feeding that environmental data into the ANN itself, so it learns to compensate automatically. But the core concept translating to hardware is very promising.
Okay, we've seen RF-PUF's strength, its properties, its simulated and even initial experimental performance. But what about the practical hurdles? We talked about the transmitter having a unique signature, but the receiver also has its own hardware, its own non-idealities. Couldn't the receiver's own signature distort the incoming signal and mess up the identification?
That's a very sharp point and absolutely a critical challenge for practical deployment. If the receiver's own quirks interfere too much, it could indeed mask the transmitter's true signature.
So how do they address the receiver's signature?
The paper proposes a couple of clever approaches. One is a loopback analysis. The receiver could essentially test itself, transmit a known signal internally, and analyze how its own circuits affect it. Then it can learn to compensate during training. Another, perhaps more sophisticated method is shown in Figure 9. It actually uses the second neural network.
A second one, what for?
This second, auxiliary ANN, is specifically trained to learn the receiver's non-idealities. It takes the features extracted from the incoming signal and performs transformations on them to effectively subtract or compensate for the receiver's distortion. Then those cleaned-up features are fed into the main identification, ANN.
So it's like a dedicated filter that removes the measurement tool's bias before the actual measurement is analyzed.
Exactly, a smart calibration filter.
And does this compensation make a big difference?
A huge difference. Figure 10 illustrates it dramatically. Without receiver compensation, the probability of falsely accepting an imposter could jump to 10-2, 1%, with just 25 transmitters. Not great.
But with compensation?
With compensation, that error rate plummets back down to 10-6, 0.0001%. Even when scaling up to over 8,000 transmitters, the error rate with compensation stays around 10-2, which, as they note, is still quite acceptable for many smart home applications.
So compensating for the receiver is crucial for maintaining high accuracy in the real world.
Absolutely essential for reliable deployment. It shows they've thought through the practical system-level issues.
Okay, practical hurdles addressed. What about deliberate attacks? No system is perfect. The paper discusses attack models for strong PUFs, PUF reuse, and malicious PUF models. How does RF-PUF stack up?
It's inherently quite robust against the malicious PUF model. That's where an attacker tries to simulate the PUF responses in software. Or maybe they physically implant a Trojan to log all the challenge response pairs. RF-PUF resists this well because, as we said, there's no digital signature stored anywhere to be easily copied or logged. The secret is the analog physical nature of the RF transmission itself. There's nothing simple to steal digitally.
Okay, but what about PUF reuse models? Like replay attacks. An attacker records a legitimate transmission and just plays it back later. Figure 11 shows this.
Replay attacks are always a theoretical concern. An adversary intercepts a message from a legitimate device, Alice, and tries to replay it, hoping the receiver thinks it's still Alice transmitting.
Can they mimic Alice's unique RF signature by replaying?
This is where it gets incredibly difficult for the attacker due to the physical nature of RF-PUFs. To successfully mimic Alice's RF fingerprint, the attacker would need to do several things with near-perfect precision in real time. First, their own receiver would need to capture Alice's signal perfectly, compensating for its own non-idealities. Then, when replaying, their own transmitter would need to perfectly compensate for its inherent signature, effectively erasing its own fingerprint, and then perfectly imprint Alice's unique RF signature onto the replayed signal.
That sounds complex. More than just copying bits?
Far more complex. It requires manipulating subtle analog RF characteristics with extreme fidelity. You need incredibly high-speed, high-resolution ADCs and DACs to capture and recreate these minuscule voltage and timing variations without introducing any detectable errors. The paper argues this makes it extremely costly and practically infeasible. Any tiny imperfection in that complex analog mimicry would likely be detected by the receiver's sensitive machine learning model. It's like a bad impressionist. The subtle flaws give them away.
Okay, that makes sense. Physical mimicry is hard. But what if the attacker uses machine learning themselves? What if they observe lots of transmissions from Alice and try to build an ML model to predict her RF fingerprint for new messages?
That's a valid theoretical attack vector ML-based modeling. However, RF-PUF's defense here is again that massive challenge response space. Remember, 280 possibilities. For the attacker, trying to learn this mapping from observed data becomes an unsupervised learning problem, which is much harder than the supervised learning the legitimate receiver uses, since the receiver knows which device is which during training. The attacker has to try and build a predictive model based only on observing outputs. Given the sheer number of possible outputs, CRPs, they would need an astronomical amount of data. The paper cites other research estimating that modeling just 1 million CRPs took 267 days on a specific processor. To model the 1024 or 280 CRPs relevant to RF-PUF would take, quote, several years of immense computation.
So it's likely infeasible due to the time and resources required.
Pretty much. By the time they could potentially model it, the technology or the device might be obsolete anyway. The sheer dimensionality provides strong practical protection against ML modeling attacks.
To wrap up the security analysis, the paper uses standard metrics: false acceptance rate, FAR, and false rejection rate, FRR. How did RF-PUF compare?
Figure 12 shows a comparison with other types of PUFs. RF-PUF performs quite well, especially for smaller numbers of transmitters, showing a good balance between FAR, letting imposters in, and FRR, blocking legitimate users.
And there's a trade-off between those two.
Always. In any authentication system, you can tune the sensitivity. You can set the protection threshold in the machine learning model. If you make it very strict, low FAR to prioritize security, you might slightly increase the chance of rejecting a legitimate device, higher FRR. If you make it more lenient, lower FRR, for convenience, you might slightly increase the chance of accepting an imposter, higher FAR.
So you can adjust it based on the application. High security for a medical device, maybe more convenience for a smart light bulb.
Exactly. This flexibility to tune the RFR trade-off is crucial for the diverse range of IoT applications. The fact that RF-PUF offers competitive performance on these standard metrics and this tunability makes it a very practical contender.
Okay, let's pull back and look at the big picture here. We've taken a pretty deep dive into RF-PUF. So to quickly recap, it's this really revolutionary approach to IoT security, using the device's own inherent physical RF characteristics, its fingerprint, as its identity. The huge advantage. No extra hardware, no extra power needed on the simple transmitter device. That's massive for IoT scale.
Game-changing.
It cleverly uses existing receiver components, adds a smart machine learning framework at the receiver for high accuracy, and does it all without needing fixed preamble.
Right. It's a really elegant example of turning those manufacturing imperfections into a security strength, rethinking physical identity.
And you mentioned it's particularly good for asymmetric IoT networks.
Yes, think about those scenarios where you have potentially thousands, maybe millions of really simple, cheap sensors out in the field. Environmental monitors, asset trackers, smart buttons, all reporting back to one powerful central gateway or a base station. RF-PUF is perfect for that. It puts the security burden, the complexity, the computation at the powerful gateway, not on the tiny, resource-starved sensors.
Which makes scaling secure IoT much more affordable and practical.
Exactly. It aligns the security architecture with the network's natural asymmetry.
And we should definitely give credit where it's due. This work comes from that team at Purdue University, Vaibhav Chatterjee, Debayan Das, Shovan Mehdi, and Shreya Sen.
Yeah, a strong team with deep expertise across hardware design, mixed signal circuits, and security. That combination is clearly what led to this kind of innovation.
So this is a fantastic foundation, but research never stops. Where does RF-PUF go from here? What's the future work?
The paper points to several key directions. They want to develop even better ways to compensate for the receiver's signature, making it even more robust. They're also looking into circuit techniques to add features like erasability and certifiability. These could potentially help thwart more advanced PUF reuse attacks by allowing signatures to be securely managed or validated offline.
Okay.
And critically, they need more formal validation against a wider range of sophisticated attack models. Plus, really thorough long-term stability analysis. How does the RF signature hold up over years across wide temperature ranges and voltage fluctuations in the real world? That's crucial for deployment confidence.
So still important work to be done, but the foundation looks incredibly strong.
Absolutely. It's just the beginning, likely, for this type of physical layer security.
Which leads us to a final provocative thought for you, the listener.
If every single wireless device, right down to its unique physical manufacturing quirks, has this verifiable RF signature, what does that really mean for anonymity in the IoT? Could this tech, down the line, let us not just authenticate devices, but maybe trace their exact origin, provide an unalterable hardware-based chain of custody, and maybe even go beyond security? Could we predict device failures or detect tampering just by monitoring subtle drifts in this physical fingerprint over time?
Imagine your smart home or critical infrastructure, not just knowing what device is talking, but having irrefutable proof of who that device physically is down to its silicon atoms, and maybe even monitoring its physical health through its radio voice.
It's a fascinating thought, isn't it? The implications stretch far beyond just preventing unauthorized access. It could fundamentally change how we think about trust, identity, and even maintenance in our increasingly connected world. #outro.
Well, that was our deep dive into RF-PUF, a truly cutting-edge technology that, honestly, promises to transform IoT security by making the physical world itself the key, the source of unbreakable identity. It really is a brilliant example of how embracing imperfection, turning a perceived flaw into a fundamental strength, can lead to groundbreaking innovation. It redefines security possibilities. We really hope this deep dive has given you a fresh perspective, maybe sparked some new ideas about how we secure the billions of devices surrounding us. Keep exploring, keep learning, and we'll catch you on the next deep dive.
And remember, understanding these concepts is the first step. Think about how these unique physical fingerprints might just secure all those tiny devices that make up our connected lives, and what that truly means for building a future we can actually trust.